Wouldn't you love to be able to travel in time? Authors through the ages have explored this tantalizing idea of being able to travel into the past or the future. Believe it or not, we are time traveling right now, into the future, one instant after another. But the question is, does time only travel in one direction, at one rate? Meet Alabama Slim. He's not only a great pool player, but he's a time outlaw. He's the only one you will ever see perform this particular pull shot. If we watch Slim breaking the rack in a game of 8-ball, we can easily tell if time is running forward or backward. The backward sequence doesn't break any laws of physics, but the coming together of all the right factors to make it happen is so improbable that we can use the words "never happen" and be absolutely right. In striking contrast, when two protons scatter off each other, time seems totally reversible. The backwards version looks just like the forward version. So why is this so different from playing pool? The answer is that the interaction between the protons is simple. Let's take a close look on how we experience time. Have you ever thought about the differences between future and past? The difference between free will and memory? And the difference between hope and remorse? You can narrow and focus your attention so that you observe that split second of what we call the present. The present is now. Now. Well, you get the point. What you're focusing on is the future flying into the past. And if you can remember it, it is no longer in the present. The present, where everything happens, seems to have no extent at all. Something that happens 1 second ago is already the past. And this is true for a millionth or a millionth of a second. Likewise, the future is as close to now as is the past. Okay, while the present is an instantaneous moment for complex objects like you and me, it can be a very different story for electrons and quarks. These particles are described by an equation called a wave function. And when two particles interact, their wave functions become entangled. But for how long? When do they reestablish their individuality? A physicist would ask, when does this wave function collapse? here's an electron named Henry bumping into one of his brothers. We know that after the interaction, Henry will be in one of two places: behind door A or behind door B. It's possible that for an extended period of time, our time, seconds, even minutes, our electron can effectively be in both places at once. Now you know why Einstein thought these guys were nuts. One way to think of this is that the electron has a flow of time that depends only on the next interaction. Present, for the simple electron, is an indefinite extension. It remains in the present until some new interaction causes it to change its wave function. And once that happens, time has moved forward. Any new interaction can cause the electron to jump from place A or place B, a light shining on, or an electric field turning on. It does not take an observation or a measurement by a person, an enduring misconception. The collapse of a quantum wave function is the point where the universe moves forward, where present becomes past, and where more than one possibility becomes just one actuality. And time itself becomes irreversible when the collapse effect spreads to enough atoms and molecules that the backward sequence becomes so improbable as to never happen. So we've discovered a possible key in our understanding of complexity. The more complexity, the more improbable it is for time to be reversible. Now let's jump from the small to the large. Here's a musician playing a ragtime piece on a guitar. At this scale, quantum mechanics is totally unnecessary to describe the scene. His atoms and the atoms in the guitar may be dancing around on a scale equal to their size, but none of that has a noticeable effect on the musician or the music. The musician has a reliable and continuous existence. There's nothing reversible in this scene, and there is uniqueness. Unlike electrons that are interchangeable, musicians are not. The probability of finding another musician exactly like this one somewhere else in the universe is virtually zero. Also notice the chance of this musician being able to travel backward in time is equally zero. Since his atoms are dancing about, continuously interacting, causing multitudes of wave functions to collapse, irreversibly changing the possibilities into realities. There is no going back. It is precisely this irreversible and complex process that makes this musician so unique.